Hi everyone and welcome to this lecture. In this lecture I want to go over diagonalization. So the last lecture we learned about eigenvalues and eigenvectors because that's what we're going to be using to diagonalize a matrix if it is diagonalizable, and we're going to go over all that. So the question is, for a square matrix A, does there exist an invertible matrix P such that P inverse times A times P is a diagonal matrix? Again, a diagonal matrix is a matrix that has entries only on the diagonal. Now, before going through the examples and definitions, let's go over this note. Two square matrices A and B are similar. Please remember that. So similar matrices. When there exists an invertible matrix P such that we can write B as P inverse times A times P. So if you can have that relation, then you can say B and A are similar matrices. Now, when a matrix is diagonalizable, let's go over that. When you have a square matrix, n by n is diagonalizable when A is similar to a diagonal matrix. So a matrix is diagonalizable when you can write that relation or this relation. And when you write that relation, you get a diagonal matrix. So let me go over this. That is, A is diagonalizable when there exists an invertible matrix P such that P inverse times A is a diagonal matrix. And a little note here, every diagonal matrix is diagonalizable. So because every diagonal matrix can be written as D equals to I inverse, which is just I, and that's times itself times I. So every diagonal matrix is diagonalizable. Now, what is the properties of similar matrices? Similar matrices have the same eigenvalues, and there's the proof for that. We said, well, we know B and A are similar because we can write B as P inverse times A times P here. Now, if you write the characteristic equation for B, please check the lecture on finding the eigenvalues. This is the characteristic equation for B. So it's lambda I minus B. Then you can write that as, excuse me, lambda I minus, instead of B, you can substitute P inverse times A times P. Now this matrix is just a diagonal matrix, and I lambda times I, and lambda being the eigenvalues. So it's going to be, it's lambda. Well, let's look at this note here. I did it for a 2 by 2 matrix. So we can write that as lambda times the identity matrix. So, and if that's just that matrix. Now what we can do, we can take this matrix and multiply it by I. Nothing is going to change, but we can write I as P inverse times P, and this is lambda. So we write that. However, this is just a diagonal matrix, so we can easily bring the P inverse to the front, and this would mean exactly the same thing. So all three of them, they're exactly the same. So we can say that equals to that and equals to that. Let's see why we did that. So here for lambda I, we can write this relation and nothing changes. It's the same thing. Now what we can do, we can factor out P inverse and put it in the front, and we can factor out P and put it at the end. So what's left is P inverse times lambda I minus A and times P. Now we want to find the determinant. Of course, the characteristic equation is finding the determinant and putting it equal to 0. So we learned in the chapter for determinants, or in the lecture for the determinants, that the determinant of A, B is the same thing as the determinant of A times the determinant of P. So using that, we can write this as the determinant of P inverse times the determinant of lambda I minus A times the determinant of P. Then this is just, these are three numbers, you multiply them, so you can put these two together. Is the determinant of P inverse times the determinant of P and times lambda I minus A. But we notice this is just I, so the matrix is I, and the determinant of an inverse, well, of the I is just 1. So again, let me repeat that. The determinant of I is just 1. So what's left is lambda I minus A. Let's notice something. We started with lambda I minus P and we ended with lambda I minus N, and they are equal to each other. So they are going to have the same roots or the same solution. So therefore, you can say that the similar matrices have same eigenvalues. Now, finding the eigenvalues of similar matrices where they have the same thing. So if you have this matrix, and if you find a similar matrix to that, I'll show you how you can do that. So you can get this diagonal matrix 1, 2, 3. We know the eigenvalues of this matrix are just the entries of the diagonal. Please check the lecture on eigenvalues. So the eigenvalues of this matrix will also be 1, 2, and 3. Now, not all the matrices are diagonal. So there are some conditions. First, an n by n matrix A is diagonalizable if and only if it has n linearly independent eigenvectors. So when you find the eigenvectors, they have to be linearly independent. Now let's go over the steps in how to diagonalize an n by n matrix. First, you have to find n linearly independent eigenvectors, and we call them P1 dot 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 Pn for A, if possible, because sometimes it won't be possible with corresponding eigen. So you first find the eigenvalues, then you find the eigenvectors, and you call them P1 dot 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 Pn. So now be careful. If n linearly independent, this means linearly independent eigenvectors do not exist, then A is not diagonalizable. So once you find the n linearly independent eigenvectors, then you form the matrix P. And the columns of that matrix are just going to be your eigenvectors. And don't forget, these are all linearly independent. So the diagonal matrix D then can be written as P inverse times A times P. So you first find P, then you find the inverse of P, then you can double check that relation, see if you get a diagonal matrix. So now that matrix that you found of, I just said that will have the eigenvalues lambda 1 to lambda n on its main diagonal. Let's look at this example. So you're given a square matrix, 3 by 3 matrix. So what you need to do first, I didn't do it here, but I just put the answer. Please double check the lecture on eigenvalues. So if you find that you get 3 different eigenvalues, if the eigenvalues are different, then for sure the eigenvectors are going to be linearly independent. So then what you need to do is one by one to find the eigenvectors. You first take the first eigenvalue, then you do 2i minus a, and so what you need to do is to uh, find the homogeneous system and find it. It's basically what you need to do is to find the null space of this matrix 2i minus a or a minus 2i. So 2i minus a here is going to be, you just take that matrix. So 2i, because the eigenvalue is I 2 times 1, so you just, all fast way of doing this, you just do 2 minus 1 here, 2 minus 1, and that's going to give you 1. 2 minus 3 is going to give you -1, and 2 minus -1 is going to give you 3. And find a basis for the null space of this matrix. Basically, that's when you solve the homogeneous system. You don't have to write the system, just find the RREF. And just to refresh your memories, here we have one free variable, and that free variable is x3. So I called it t. Then if you rewrite the system, you get x1 minus x plus x3 equals to 0. So x1 will be negative x3, so that's negative t. And x2 from here, we know it's going to be 0. So if we write the components, it's negative t, 0 t. You can factor out t, so you get -1, 0, 1. And that's p1. So that's a vector in the basis of the null space, and that's basically how you find the eigenvectors. So we have p1. Then you can do the same thing with lambda 2. You can write negative lambda, which is -2. So you write -2i minus a. So again, -2 minus 1, -2 minus 1. Here, -2 minus 1 is going to give you -3. And -2 minus 3 here is going to give you -5. And -2 minus 1 is going to, -2 minus -1 is going to give you -1. Same way, what you can do, find the RREF of this matrix and find a basis for the null space. Here we have again one free variable. If you do that, then the basis is going to be 1/4, -1/4, 1, or any scalar multiple of this vector will be a vector in the basis of the null space. And to avoid fractions, what you can do is take the 1/4 out, so you get 1, 1, and 4. But these are exactly the same. You can even use this one. Then you can do the same thing with lambda 3. So lambda equals 3, which is equal to 3. So do the same thing. 3i minus a is going to give you that matrix. The RREF of that is going to give you that. Again, x3 is a free variable here. You can rewrite the system, and if you do that, then you can find p3, which is -1, 1, and 1. So you can write the matrix P. Again, this was P1. So -1, 0, 1. And let me double check that. -1, 0, and that should be 1. And P2, we found that to be 1, -1, 4, and P3 was right here. You can see this 1, 1, 0. Now we found our matrix P. Once you get that, find the inverse of that matrix and then check that relation. So if you multiply P inverse times A times B, you are going to get 2 in the diagonal entry is going to be 2, -2, and 3. And again, as we noticed, these are all eigenvalues of our original matrix. So I think that's it for this lecture. Please try one or try the same example, write the matrix down, and then do all the details. If you forgot, check the last videos, find the eigenvalues, find the eigenvectors for the corresponding eigenvalues, and do the matrix multiplication and see if you get that relation. So have a good one, everyone, and I'll see you in my next video or next lecture. Thank you for watching.